Hey there. In this video, we're going to be talking about systems of differential equations. Now, systems of equations involves linear algebra. So you should review linear algebra, make sure you're up to speed with the basics of that. I'm going to go through some basics, just what we need to know to kind of get through the things that we're doing, but you're going to want to have a little bit more understanding to be able to make a complete picture out of everything. All right, so make sure you review your linear algebra before we watch this video. Okay, so we're going to start with an example of systems of differential equations. So let's go ahead and take a look. The example I have here asks us to consider a situation where fluid is transferring between two tanks. And we want to derive a system of differential equations for the quantities of salt in the tanks at any time t. So you can see what's going on here. In tank 1 over here, we've got some amount of fluid. We got 100 gallons. And fluid is entering tank 1 at 5 gallons per minute and at 1 pound of salt per gallon. And fluid is leaving tank 1 at a certain rate, and it's leaving into tank 2 at a certain rate. Okay, and then look at what's happening with tank 2 over here. We got salt water coming in, 4 gallons per minute at 2 pounds per gallon. And we have water draining out of tank 2 and also draining out of tank 2 into tank 1. So there's an exchange between the tanks as well. Okay, so what we're going to do is try to write a system of differential equations that describes this scenario. So here we go. We're going to let y1 and y2 denote the quantities in pounds of salt in each tank. Okay, so y1 will denote just the amount of salt in pounds in this tank, and y2 will denote the amount of pounds in salt in this tank. So let's write down an equation for tank 1. Well, in order to write this down, we have to think about how do I measure how much salt is coming into tank 1. All right, well, if I look here, I've got 5 gallons per minute and 1 pound per gallon. Multiplying these together gives me pounds per minute. That's the rate at which salt is entering tank 1. So that tells me information about the rate at which salt is entering. So the rate in is 5, right? Coming from this source right here. However, we also have another source coming into the tank. We have this coming in from tank 2. That's coming in at 3 gallons per minute. Now we need to multiply that by the concentration to get the pounds per minute of salt. So what's the concentration that the source of the source? Well, the source is tank 2, and to get the concentration, we're going to take the amount of salt in tank 2 and divide by the amount of fluid in tank 2. That gives us the concentration. We're going to multiply that by the rate it's going into tank 1. And that's exactly what I did here. This is the concentration. Amount of salt in tank 2 is what we're calling y2. Divide by the amount of fluid in tank 2, that's 300 gallons, and then multiply by the rate that it's going into tank 1. Now keep in mind, we're using the fact that the amount of fluid in these tanks is a constant. Notice that the amount of fluid leaving tank 2 is, there's 3 in this direction and 3 in this direction, and then that's a total of 6, and there's 4 in this direction and 2 in this direction. That's a total of 6. So the fluid level's remaining constant, and that's why I can just put a constant down here in the denominator. The fluid level's not changing. If the fluid level were changing, we'd have to think a little bit more about this. Okay, so here we have our rate in. What about the rate out? Well, the rate out of tank 1 is the concentration of salt in tank 1 multiplied by the rate at which fluid is leaving tank 1. It's going to be pounds per gallon multiplied by gallons per minute. So we're going to take the concentration, which is the amount of salt in tank 1, we denote that by a y1, divide by the amount of fluid in tank 1, which again is a constant, always equal to 100. That's the concentration. And I'm multiplying by 8. Where did I get 8? Well, you see 6 gallons per minute going this way, but then an additional 2 gallons per minute going this way. In total, that's 8. So here we have the rate out of tank 1. All right, so we put these together to get our rate of change for tank 1. The rate at which the amount of salt is changing is rate in minus rate out. put those together, these two expressions here, and we get a differential equation for y1. Now we do the same thing for tank 2. All the considerations are the same, so I'll go through it quickly. We compute the rate in. We've got, into tank 2, we've got 4 gallons per minute at 2 pounds per gallon. Multiply those, you get 8, right? But then we also have salt coming in from tank 1. That's this quantity here, concentration times the rate. So that's the rate in. What about the rate out of tank 2? Well, the rate out of tank 2, we've got 3 gallons per minute going this way and 3 gallons per minute going that way. A total of 6 gallons per minute, that's my 6. Multiplying that by the concentration of salt in tank 2, which is the amount divided by the amount of fluid in tank 2. So we multiply those, that gives us the rate out. The rate of change for tank 2 is therefore rate in minus rate out. And so we get this differential equation. Putting those together gives us a system of differential equations. So this type of problem is precisely the problem that we want to deal with. But the question is, how do we solve this? Now, we're not going to go through the full details of how to solve this in this video. That'll be in a later video. But we're going to talk about the fundamentals to get started. Okay? Before we do that, I almost forgot, I wanted to show you a little bit of little diagram about what's going on here. When you get this system, even though we can't solve this, one thing we can do is we can investigate the solution. We can make a vector plot based on this differential equation here. So I did that. Okay, so what we're looking at here is a vector field given by the differential equation. Okay, so what you're seeing on the horizontal axis, which is off the picture here, I can't really get it on, is representing the y1. That's the amount of salt in tank 1. And the vertical axis here is representing the amount of salt in tank 2. So if I specify a point here, what I'm doing is I'm specifying the initial amount of salt in tanks 1 and tank 2. And then as I follow the direction field, it's telling me how those amounts of salt are changing. So you can see, if we start with an initial amount of salt around here, so the amount of salt in tank 2 is a little above 400. Can't really see the bottom axis here. I think it's around 50 in tank 1. We can see that the amount of salt is going to be increasing in tanks 1 and tank 2. However, if I pick a different starting point, we can see that the amount of salt in tank 1 is going to be increasing, but the amount of salt in tank 2 is decreasing. And various points we can see different things happening. So we can get a kind of an idea for what is happening with this differential equation by looking at this plot. Of course, this isn't a rigorous concrete solution, but it's something to kind of get an idea of what's going on. And again, this vector field just came directly from this system right here. But let's go on and talk about the fundamentals of how to solve these things algebraically without just kind of guessing by looking at a vector field. Well, how do systems of equations work? Okay, well, here's a system of equations, and my variables are x1 and x2, right? Well, one thing I can do with a system of equations like this is I can rewrite it in matrix form. And this is where you might want to review linear algebra if you're not familiar with this. So you can rewrite this system as a matrix multiplied by a vector whose components are x1 and x2, and that's equal to another vector. So I can write it in this form. Now, just to compress that into a nice abstract form, we represent the matrix by a letter A, the vector x1, x2 by x with an arrow over it, and this vector here with just by a vector B. So this whole thing is in this form. This is a matrix equation. What about differential equations? Well, here we go. Something like we had before, y1 prime and y2 prime. We have a linear system here. Well, we could do the same thing. I'm going to view my vector as the vector y1, y2. So here it is, multiplied by a matrix to get this. Now notice the components of the matrix here, some of them depend on t. That's the same variable that y depends on. So that's something we'll be considering. These don't need to be constants. They can depend on t. And then what is this? y1 prime and y2 prime. That's also can be viewed as a vector. And we can just encapsulate that all down to this form here. My vector y represents y1, y2. And if I write y prime, what I mean is the vector consisting of y1 prime and y2 prime, right? Just as you'd expect. And so we have a matrix, a function of t multiplied by this vector gives us this system. Okay, so some of the machinery here. One of the things that we're going to have to come to terms with is what a linear combination is. We're going to be using this. A linear combination of vector functions. You're going to multiply each vector by a constant and then add them together. And if you do that, that's called a linear combination. So a set of vectors are said to be linearly dependent if some yi, just one, any yi, can be written as a linear combination of the other yj's. So for example, here's a set of vectors. These are linearly dependent. It's not immediately obvious by looking at them, but check this out. y3 can be written as a linear combination of y1 and y2. Right? y3 is my yi, and the yj's are my y1 and y2 in this case. And if you look, y3 is exactly twice y1 minus y2. Go ahead and check it. You'll see you get y3. So since y3 can be written as a linear combination of y1 and y2, this set is linearly dependent. Now, a set is said to be linearly independent if they are not linearly dependent. Okay, so that's what linear independence means. Gotta move, dodging everything over here. Now we have a theorem. Okay, the vectors y1 through yn are linearly independent. If they are independent, then a linear combination of them can be 0 if and only if all of those constants were 0. So the only way you can get a linear combination of linearly independent vectors to be 0 is if you make all of these constants 0. So this will be a handy theorem for us. And this is a theorem that you can actually prove from the definitions that we just talked about for linear independence and dependence. So it'd be a good exercise for you to prove this theorem. It's totally doable. It's not very hard. A set of solutions to a system is called a fundamental set if every solution can be expressed as a linear combination of those solutions. So when we solve differential equations, we're going to be finding solutions. And we want to know when we have enough solutions that we can express any solution in terms of those. Well, once we have that set, that's called a fundamental set. So now we can write down any solution just in terms of those. So this is something we're going to be looking for when we solve differential equations, trying to find that fundamental set, because from there we get everything. So here's an example. This isn't obvious, all right, but this set of vectors here is a fundamental set for this differential equation. Now it's not, it'd be a good exercise for you to verify that these vectors solve this differential equation. Just take them, take the derivative, take the matrix, multiply it by it for each of these two vectors, just verify that that's true. And you'll see that it is. So these solve this differential equation. Now, how do we know they're a fundamental set? Well, we can't tell yet. We're going to learn in the next slide, all right? But just for instance, what does it mean to be a fundamental set? Well, it means that if I take any solution, this is also a solution to this differential equation. And you can check that, take the derivative, and then multiply it by the matrix, verify that they're the same. You'll see that it works. That means that I should be able to express this as a linear combination of these guys. And sure enough, I can. I can write this as 5 times the first one minus 3 times the second one. If this is a fundamental set, I'm always guaranteed to be able to do that. Now we have a theorem. Suppose the n by n matrix, that means it has n rows and n columns, A, is continuous on an interval. Now it's a function of t, so we can talk about its continuity. And what that means is that each of its component functions is continuous. Then a set, y1 through yn, of n solutions of that differential equation. Now this n and this n are the same. They need to be the same. Is a fundamental set if and only if it is linearly independent. So this is why we talked about linear independence. To verify that something is a fundamental set, all we need to do is verify that it's linearly independent. So for instance, to show that this was a fundamental set, what we would need to do is verify that these guys are linearly independent. And you can actually do this on the interval negative infinity to infinity. How do you do that? Well, we're getting there. Here's a theorem. Vectors are linearly independent if and only if the matrix comprised of column vectors has a non-zero determinant. So this is a way we can check to see if they're linearly independent. Now you could actually go back to the definition that we talked about early on, and that would work, but that's a little bit tedious. All right? This is a really nice way to check for linear independence. And determinant is one of these topics that you might need to review. I'm not going to go over it here. Okay? So it's a linear algebra topic. You may need to go over that. All right, so for example, to show that this is a fundamental set, we need to verify that these are linearly independent, but that theorem says that we just need to verify that the determinant is non-zero. And if I want to show it's linear independent on this interval, negative infinity to infinity, I need to verify that the determinant is non-zero on that interval. Well, we can do it. Let's do it. Computing the determinant. So what I did, by the way, what I did is I multiplied this into the vector. So 1 multiplied by e to the 6t became e to the 6t, e to the 6t, right? Same thing here. I multiplied this into the vector to get this matrix. So let's compute its determinant. For a 2 by 2 matrix, determinants are really easy. You just multiply down this diagonal and then subtract what you get when you multiply down that diagonal. So this minus this. And that's exactly what I did here. When you do that, you get minus 2 e to the 4t. Can that ever be 0? No, that can never be 0 because e to the any power can never be 0, right? So that means this is never 0 for any value of t, which means that this will always these will always be linearly independent. They'll always be a fundamental set everywhere. So we can do it from minus infinity to infinity. If there was a 0, we'd have to stop there. We wouldn't be able to include that in our interval. The determinant of this matrix that we made out of our vectors is called the Wronskian. The Wronskian. So here's a theorem. Suppose the n by n matrix A is continuous on an interval. Let these vectors be solutions of the differential equation on the interval. And let t0 be any number in that interval. Then the Wronskian of those solutions is given by this. Now, we had a formula for the Wronskian. We take the determinant of the solution vectors. But this is saying that there's another way to get the Wronskian. It's saying that you can just evaluate the Wronskian at this value t0, and t0 can be any number in the interval, and then you multiply it by e to the integral of this stuff. What's that stuff? Well, those are the components of A. When you have a matrix A, you can we can just label the components of that matrix, and we label them with subscripts going from 1 to n. The first subscript tells you the row of the matrix. The second subscript tells you the column of the matrix. So we have n times n components here. What are the components that you see here? These are the components down the diagonal of the matrix. When you add the components down the diagonal of a matrix, that's called the trace of the matrix. And it's denoted TR sometimes. Sometimes they put a superscript T here. The trace of a matrix is just the sum of the diagonal elements. And that's what this is saying. It's saying the Wronskian can really be determined by the integral of the trace of the matrix that we started with. Now this is a very powerful theorem because what it's saying is that just by knowing that we have that the Wronskian is non-zero at some point t0, this is telling us that it's non-zero everywhere in that interval. So we only need to check that it's non-zero at one point, and therefore it's guaranteed to be non-zero everywhere, because e to something can never be 0, and this is just a constant. So, but without this theorem, we might be worried that we start with a fundamental set of solutions, right? And they're all linearly independent. But as we change t, they might change and become linearly dependent. We don't know that that couldn't happen a priori. This theorem is saying that as long as we have continuity, it can happen. If they start linearly independent, they have to stay linearly independent. So here's an example. Even without solving the differential equation, just by looking at this, we can compute the Wronskian up to a constant. And so I'm just going to use this formula. So what I'm going to do is I'm just going to use this formula. W of t 0, I would need to know some solutions, right? So there's some constant here. And then on e to the what? Well, this is the trace of my matrix. That's just 2 plus 2, just summing the diagonal elements. Well, that's just, if I integrate that, I just get this. And I can pull out this constant here. This whole thing involving t0 is just a constant. So I just get a constant times e to the 4t. Right? So I can determine the Wronskian up to a constant. Where would I get this stuff? I would get that from the set of solutions evaluated at t0. And that is it. So a bunch of introductory stuff. We will talk about how to use this stuff to actually get the solutions to our differential equations in the next video.